Here's a short lecture in Chapter 5 to help supplement what we've introduced in the first lecture in Chapter 5. Consider this example problem of applying Newton's second law. Two masses, 3 kilograms and 5 kilograms, are connected by a light string passing over a frictionless pulley. Determine the acceleration of each mass and the tension in the string. Alright, so we have two masses, 3 and 5, and they're connected together, and we know that the string is going to be taut, so there's going to be tension pulling inward on both ends of the string. So mass 1 is going to have tension pulling up, and mass 2 is going to have tension pulling up on it as well. The tension will be consistent all the way through this string. And we know it will move together, and we have pretty good intuition that 5 kilograms is greater than 3 kilograms. So this whole thing is going to move in one direction, with the 5 going down and the 3 going up. And so there'll be one value of acceleration, even though mass 2 will go down and mass 1 will go up. They'll have the same value of acceleration, the same speed, and all the same kinematics involved as they're moving. So it's assumed mass 2 is heavier than mass 1, the tension is constant. If I were to make a free body diagram of mass 1, I would say, well, tension's pulling up, its weight, m1g, is pulling down, and as a result of all these external forces acting on mass 1, it manages to accelerate up with some value a of acceleration. That would be my free body diagram of mass 1. Those are all the external forces. I just focus in on mass 1, and those are the only forces acting on mass 1, and the resultant acceleration is in the upward direction. I want to do the same thing for mass 2. I want to make a free body diagram of mass 2. Here it is. Mass 2, tension's pulling up, m2g is pulling down. As a result of all these net forces acting on mass 2, it manages to accelerate down with a value of acceleration a. So these are my free body diagrams, and the reason I want to make good free body diagrams of my masses is so that I can set up my Newton's second law equation based on these free body diagrams. So looking at the free body diagram number 1 for mass 1, I set up my Newton's second law equation. The summation of all the forces acting in the y direction of mass 1 is equal to my net force, mass 1 times acceleration, and that's equal to the net force in the direction of acceleration. In this case, my positive direction will be up because that's the direction of my acceleration. So that's going to be tension minus m1g. So that's my first equation based on that. Now I have the other free body diagram, and this is for mass 2, and I see that my acceleration is down, so that is my positive direction, down direction. And so if I were to set up my Newton's second law for that, I would say the net force on mass 2 is equal to m2a, mass times acceleration, and that should equal all the external forces added up that give me a net force in the direction of acceleration, which in this case my positive direction is down. So that's going to be m2g minus tension, net force in the down direction. And that is my second equation. And both these equations, the value of acceleration is the same. So I have two equations with two unknowns. I'm going to add them together. I'm going to add everything on the left-hand side together, everything on the right-hand side together. They're equal, so that I should be able to do that. So mass 1a plus mass 2a equals tension minus m1g plus m2g minus tension. The tension minus tension cancels out. And factoring out the a on the left-hand side, I have mass 1 plus mass 2 times a. And factoring out the g on the right-hand side, I have m2 minus m1 times g. Or my acceleration is mass 2 minus mass 1 times g over mass 1 plus mass 2. And that's my acceleration for this general situation of two masses on this pulley And so I can plug in my masses and get what my acceleration should be. Here's a check. If mass 1 were equal to mass 2, then there would be no impetus for it to move one way or the other, and it would be stationary. And we can see my acceleration would be, well, the two masses would cancel out and have 0 on the numerator here, and my acceleration would be 0, which makes sense. It wouldn't move. If mass 2 were a lot bigger than mass 1, this thing would just basically fall according to gravity. And I can see from my acceleration, if m2 were a lot bigger than m1, infinitely bigger, say, then I'd end up with mass 2 over mass 2, basically, which would be 1, and my acceleration would be g. So it would just go like that. So that makes sense. It's always good to check these things with extreme conditions to see if they make sense. So with mass 1 equal to 3 kilograms and mass 2 equal to 5 kilograms, my acceleration will be 5 minus 3 over 5 plus 3. That's going to be 2 over 8, or 1/4 of 9.8, which is 2.45 meters per second squared. Up for mass 1, down for mass 2 for my directions. To find the tension, we can plug this acceleration back into either of those equations and solve for the tension. Looks like I chose equation number 1. So mass 1A, mass 1 times A is equal to the tension minus m1g. I know the acceleration now. I know g is 9.8. I can solve this for the tension. So 3 times 2.45 is equal to tension minus 3 times 9.8. So tension will equal 3 times this plus 3 times 9.8. That's going to be 29.4 plus 7.35, or 36.75 newtons. That's the tension in the cord. If I plug this acceleration back into the other equation and solve for t, I would get the same answer, 36.75 newtons. Here's an alternate method for approaching this problem. Let's look at this combined mass 1 plus mass 2 as one blob of mass. We're just going to blob it together as one mass. That's one total mass, m1 plus m2. If I do that, I can treat this whole system as one mass moving under one acceleration in one particular direction. It's kind of a curved direction, but it's kind of moving like this as one mass. And so I want to look at the external forces acting on this one mass. I'm going to set up Newton's second law, a free body diagram, looking at the external forces acting on this one mass in the direction of motion. Well, I've got a total mass, m1 plus m2. I got an m2g pulling on it on one end, m1g pulling it on the other end, and one's bigger than the other, so the m1g is kind of slowing it down as it's moving in this forward direction. I got one acceleration going along this whole direction, and that's in the forward direction. So if I were to apply Newton's second law to this total blob of mass, I would have the total mass, m1 plus m2, times acceleration, that's my net force, is equal to the net force in the direction of acceleration. So that would be m2g minus m1g. I don't have to worry about tension because that's internal to this blob. It's inside the blob. It's part of the whole system now. I might want to worry about the normal force or the weight at the pulley, but those are going to be perpendicular to the direction of motion, so they'll be transverse. They add up to 0 in that direction. So as far as the acceleration direction is going, this is what I have going on. So right away, I would have 8 times a is equal to 5g minus 3g. Acceleration is going to equal 2 times 9.8 divided by 8, or 2.45 meters per second squared. It's a quick way of getting the acceleration if that's what you want. That gives you more information on the problem, and then you can look at the problem more closely at one mass or the other to solve for the tension. But this allows you to get the acceleration right away and allows you to get more information on the problem, making the problem a lot easier. So you want to employ this method on a lot of the problems that you would you would encounter in the problem sets. We also wish to introduce another force, a force of friction. Consider this. Friction is actually a good thing. It allows us to walk, and it allows us to actually have wheeled motion as well. The reason this works is by Newton's third law. If I'm walking along like this, the reason I'm able to propel myself forward is because I exert a force in that direction, and by Newton's third law, the floor exerts a force back on me, and it allows me to move forward. So I push one way, the force of the floor pushes back, and it pushes me forward. So if I didn't have friction, which is allowing the force of the floor to do that, if I didn't have friction, I would just slip and never move forward. You're like walking on ice. You would never have a chance to move forward. So the friction allows you to apply that force, allows you to propel forward, and allows walking to occur, allows wheeled motion to occur. Negative consequences of friction is that if you're sliding, the friction will work against you as you're sliding. So if you have any kind of velocity, any kind of motion in one direction, friction will slow you down. And that's what we're going to be looking at here. So it hinders sliding motion, and in fact, in doing so, it also dissipates energy in the form of heat, and it heats up, and that could be, you're going to lose energy, mechanical energy, because of that. Turns out that the frictional force, whether it be static friction or kinetic friction, static is the friction that occurs when everything's still stationary. Kinetic is when the frictional force that occurs when the object is moving. Both of these forces are proportional to the normal force. So whatever the normal force is of the surface on your object, the frictional force is proportional to that. And the factor of proportionality is called the coefficient of friction. The static coefficient of friction is designated by mu sub s, and the kinetic coefficient of friction is designated by mu sub k. If the object's moving, it's going to have a kinetic friction on it, and if the object's stationary, it's going to have a static friction on it. The maximum static frictional force is greater than your kinetic frictional force. So to get something to start moving, you have to overcome the static frictional force, the maximum one, maximum static frictional force, before you start getting it moving, and then your frictional force will be a little bit less than that peak. But these coefficients of friction are just numbers, and they relate how great the frictional force is to the normal force. Some percentage of the normal force is the frictional force. So there are no units on these coefficients of friction. They're just simply fractions, generally between 0.1 and 1. Sometimes they can be greater than 1, but generally they're going to be found in the ratio of around 0.1 to 1 with no units on them. They're just simply giving you a fractional proportion of how much the frictional force is to the normal force. So it might look something like this. If you're pushing on something, trying to move it, the static frictional force will equal your force, equal your force, equal your force, up until you reach the maximum static frictional force, and then it'll start to move. And when it does, then you'll be under the kinetic frictional force. So you push on it, it equals your force, you reach the maximum value, and then you have to just endure some constant, more or less constant, it's kind of a little bit rough, constant value of a kinetic frictional force. One of the best examples for me, being a Minnesotan, is when I grew up, one of the things you would do on the first snowfall, if it were sticky snow, is build a snowman. So you would roll a ball, and you start rolling the ball on the ground and start building up snow as you go, and your boulder would get bigger and bigger and bigger. And you knew that you never want to stop rolling the ball, because as you're rolling the ball, you're only trying to overcome kinetic friction. But once you stop, then it's going to be hard to overcome the static friction because it's always greater than your value of kinetic friction when you're rolling the ball. So you roll the ball, and then if you have to stop, then you decide, that's a good spot to build a snowman right there. So you have your big boulder there, and you build a smaller boulder, put it in the middle, even smaller boulder, put it on top, and you got your snowman wherever you happen to stop. Another example would be if you got your truck stuck in the mud. It's always easier to get it out if you get it rolling and moving, because then you have to overcome the kinetic frictional force as opposed to the static frictional force, as opposed to if it were just stationary at that point. All right, so we want to try this out. Here's a problem. A 9 kilogram hanging weight is connected by a string over a pulley to a 5 kilogram block that is sliding on a flat table. If the coefficient of kinetic friction is 0.2, and this system is going to be moving, so we're using kinetic friction, what will be the acceleration of this system? We want to set up a free body diagram for these blocks and then apply Newton's laws. If I look at mass number 1, it's going to have weight, m1g, pulling down to the center of the earth, and it's going to have a normal force equal to that weight going up because I'm stationary vertically. It's going to have tension pulling it to the right, but now, since it's on this table, it's going to have a frictional force opposing its motion to the right. So that frictional force is going to be to the left, as you're looking at the screen to your left. So that's going to be mu times m1g. So that is the free body diagram acting on mass 1. On mass 2, there's only two forces acting on it. We have gravity, m2g, down towards the center of the earth, and we have the tension of the core going up, and it manages to accelerate down as mass 1 is accelerate to the right. We're going to treat this as one blob of mass so that we can just find the acceleration to begin with. We use this new technique of the blob method, and that makes tension internal. M2g is going to make this go, and the frictional force on the table is going to slow it down. It's going to retard the motion. So those are the forces with acceleration in the forward direction. M2g will be a positive force, and the frictional force will be a negative force. So we have a total mass, m1 plus m2, everything going in a forward acceleration as you're looking at it. m2g at the front, mu times the normal force equal to m1g in this case, mu times m1g slowing it down. So we have our net force, total mass times acceleration, and that's equal to m2g minus mu m1g. So acceleration will equal m2g minus mu m1g divided by the total mass. That's going to be 9 kilograms times 9.8 minus mu 0.2 times 5 kilograms times 9.8 over the total mass 9 plus 5. Gives us a value of acceleration of 5.6 meters per second squared. Then if we want to find the tension, we can look at either mass, the free body diagram for either mass, and plug this acceleration in there and solve for the tension. Easiest one to use would be the mass m2 because there was only two forces on it. So if we use this free body diagram and we know the acceleration is going down, our m2a, Newton's second law, is going to be equal to the net force in the direction of acceleration, which will be m2g minus tension. And we're going to solve this for the tension, bring the tension over to the left, the m2a over to the right. So we have tension is equal to m2g minus m2a, 9 kilograms times 9.8 minus 9 kilograms times 5.6. The tension in our cord is 37.8 newtons. So by blobbing it together first, we were able to find the acceleration pretty quickly, and then we were able to find the tension pretty quickly by focusing in on one of the masses and doing a free body diagram of one of the masses, solving for the tension. Let's try one more example, one more problem. Determine the stopping distance for a skier moving down a slope with friction with an initial speed of 20 meters per second. Assume the kinetic coefficient of friction is 0.18, no units on that, it's just a fraction, and that the slope of the incline is 5 degrees. Here's our skier. So our frictional force is going to be mu times the normal force, but we know from our previous lecture that the normal force on the incline is going to be equal to mg cosine theta. So our frictional force is going to be mu times mg cosine theta. And the force going down the incline is going to be equal to mg sine theta, but now we're working against this frictional force as well. So we're going to have an mg sine theta minus the friction will be our net force down the incline. So mass times acceleration in the positive acceleration direction down the incline, it will be mg sine theta minus mu mg cosine theta. The masses cancel out, and our acceleration then will be equal to g, factor it out, sine theta minus mu cosine theta. Theta was 5 degrees, mu is 0.18, g is 9.8. So we have 9.8 times the sine of 5 degrees minus 0.18 times cosine 5 degrees. And if we plug that in, we get a negative 0.903 meters per second squared. What does a negative mean? Well, as we're going down this incline, we're slowing down. So we started with a velocity of 20 meters per second. Eventually we're going to come to a stop. And the reason we're stopping is because our acceleration is negative. Frictional value is greater than the mg sine theta. So now we can find our stopping distance by using kinematics. We have this acceleration, and we know our initial velocity, and we know our final velocity should be 0. We're going to come to a stop. So we can plug everything in and get what delta x should be. So our final velocity would be 0. And our initial velocity was 20 meters per second. Delta x will be equal to a negative initial velocity squared over 2 times acceleration. That's going to be a negative 20 meters per second squared over 2 times a negative 0.903. And that will be 221 meters. So if you were a skier, you would calculate that you come to rest finally after 221 meters. If you're in the ski jumping, then that would be the distance that you would achieve, 221 meters down the slope. That concludes this short lecture on Chapter 5, giving you a few more examples and friction to deal with. Try your hand at the problems in the problem sets and look at the examples on EduCreations to see how to work out some of those problems if you run into trouble. Good luck.